Today's lesson is focused on explaining all the steps and the procedures to graph a function. The function I've chose for today's lesson is a rational function. F of x is x minus 2, x plus 5 multiplied by x plus 5 over x plus 7 multiplied by x minus 4. For this exercise, the focus is not on deriving functions. The function is on using the derivative, so it's an application on derivatives. Therefore, f prime of x is given, and f double prime of x is given as well. If we look at the domain of the function is determined by looking at its restrictions. So f of x is a function that has a denominator of x plus 7 and x minus 4 factors. Therefore, the restrictions are x plus 7 cannot be 0, so x cannot be negative 7, and x cannot be 4. So the domain is between less than negative 7, x values between negative 7 and 4, or greater than 4. And therefore, the vertical asymptotes are x equals negative 7 or x equals 4. The end behavior, the limit of the function as x goes to positive and negative infinity, as you can see, is 1. Therefore, y equals 1 is a horizontal asymptote. As for the x-intercepts, where the y is 0 or the function is 0, so the numerator has to be 0. So x minus 2 has to be 0, x plus 5 has to be 0 for f. Therefore, the x-intercepts are x equals 2 and x equals negative 5. The y-intercept, we can find it by setting x equal to 0, and therefore y is 5 over 14. Then we determine the sign of f prime of x, because that's going to give us an idea of how's the function increasing and where, or decreasing. So we set f prime of x equal to 0, and in that case the numerator has to be 0, and the only factor in there that could be 0 is 2x plus 3. So x equals negative 1.5, we're going to write here, is a possible turning point. So y arrow possible turning point, that's because it's only determined as a turning point if we see a sign change before and after that y prime or f prime root. So drawing the number line for sign of f prime of x, we realize that the restrictions, are negative 7 and 4, we have vertical asymptotes. And at negative 1.5, that is a root for f prime of x. And now we need to determine the signs as they change. We notice that at negative 7 and at 4 on f prime of x, they're both even restrictions. The exponent is 2, so these factors happen twice, so it's an even restriction. Therefore, the sign does not change before and after that restriction. As for negative 1.5, it comes from the expression 2x plus 3, which is an odd restriction, or a single root, in other words. Sorry, not a restriction, it's an odd root or a single root, preferably a single root. So what that means to us is that there should be a change in sign before and after that root, and that tells me that since there is a change in sign, that there is a turning point here. Now we have to determine the first sign in the interval x is less than negative 7. To do that, we look at y prime or f prime of x and see that x plus 7 is squared and x minus 4 is squared, and that means that the denominator is always positive unless x equals negative 7 or 4, which in that case is restricted by the domain. So we are certain that the denominator is always positive. So who controls the sign of f prime of x is the numerator. The numerator for 2x plus 3, any value less than negative 1.5, which is the root of 2x plus 3, thinking that 2x plus 3 is a line, any value of x that's less than negative 1.5 That means that since that line has a positive slope, the line is going to be increasing, and therefore before the root, the function 2x plus 3 is negative. And there is a negative coefficient here, so negative with a negative will make a positive value, and therefore this sign here becomes positive. Now, x equals negative 7 is an even restriction, so the sign stays the same, positive. At negative 1.5, we realize that that is a single root here. It's coming from the expression 2x plus 3 power 1. Therefore, there must be a sign change, and the sign becomes negative. At x equals 4, we know that it is an even restriction. So we have a 2 on the exponent of x minus 4. Therefore, the sign has to stay the same. And now for f of x will be increasing for x is less than negative 7, increasing between negative 7 and negative 1.5, decreasing between negative 1.5 and 4, and decreasing as well for x is greater than 4. We've just determined here that there is a max at negative 1.5, and the y value, by summing into the f of x, we could determine it's 0.405. And those are the intervals of increase and decrease. As you can see, they are matching the arrows up, down for f of x. Then we need to determine the sign of f double prime of x by setting first f double prime of x equal to 0 to determine the possible inflection points. But in this case, f prime of x can never be 0. The numerator, 36, definitely cannot be 0, but 3x squared plus 9x plus 37 is a quadratic function that has no roots in set R. Therefore, the function is, since its positive leading coefficient exists here, it's entirely above the x-axis and therefore always positive. Now, to determine the sign of f double prime of x, we draw the number line. We do not have any possible inflection points, so the only thing that we can put on that number line are the vertical asymptotes. Again, we need to determine the sign as x goes to negative infinity, and we could figure out the rest. Keep in mind now, and in f double prime of x, x equal negative 7 is an odd root. The exponent is 3. And x equal 4 is an odd root as well, with an exponent of 3. So there must be a change of sign before and after these vertical asymptotes. As for the sign as x goes to negative infinity, we look at the numerator. The expression 3x squared plus 9x plus 37 is always positive. As we've discussed, no real roots, positive leading coefficient, so the function opens up. The vertex has to be above the x-axis. Therefore, it's always positive. Times 36, which is positive. Therefore, the numerator is always positive. Who determines the sign is the denominator. Now, x plus 7 is a linear function on its own. So if x is less than negative 7, which is the root for x plus 7, that function, with a positive slope, must be negative, and at negative 7 it's 0, and after negative 7 that function becomes positive. Therefore, cubing a negative stays negative, cubing a positive stays positive. So as x goes to negative infinity, that whole expression x plus 7 power 3 on f double prime of x is always a negative value. Same goes for x minus 4 power 3. If x is less than 4, so as x goes to negative infinity, that whole expression is negative. Negative cubed is negative. Now, when we have two negative terms in the denominator multiplied, they give us a positive outcome, and therefore positive numerator over positive denominator gives us positive f double prime of x, as x goes to negative infinity. Now, at negative 7, at x equals negative 7, we've identified that since this is a degree 3, same as that, these are odd restrictions, so the sign must change to negative, then to positive. And now for f of x, we see the concavities up, then down, then up. Those are the intervals of concavity up, x is less than -7 or x is greater than 4. Intervals of concave down is between -7 and 4. To put the drawing and connect all these information together, we put the xy axes, put the roots, -5 and 2, put the vertical asymptotes at -7 at 4, put the horizontal asymptote at y equals 1, put the y-intercept and the maximum value, and we start following the f prime of x. So the first thing we look at is f prime of x. The function is increasing for x is less than -7. So anything less than -7, the function has to be increasing, and the concavity must show up. Since there is a horizontal asymptote, we have to start close to the horizontal asymptote. We cannot start below, because if it starts below, the function must decrease before it can increase. And since we only see on f prime of x an increasing interval, therefore that function is strictly moving up. For the second interval between -7 and -1.5, the function is also increasing. So as we see from the graph, there is a sign change here. So as the y went to positive infinity, then the y will start from -infinity. And it's also increasing. And now notice the concavity changes. The concavity as x less than -7 was up. But the concavity after -7 is down. And we see that here. The graph will increase, go to -5, cross. This is a single root, so the function will simply cross through. And again, the exponent here is 1, the exponent here is 1, and here also, and here also. So those on the function, these are odd restrictions, odd vertical asymptotes. And as a result, there must be a sign change before and after them. So we look here, we see the sign change on the vertical asymptote. It has to start from -infinity, go through the root, go to the max, go to the y-intercept, back to the root. Again, the root is a single root, so go through and down to -infinity. Now x equals 4 again comes from here. That's a single restriction, so the sign will change. And again, the function is decreasing after x equals 4. So again, we'll go down to the horizontal asymptote and notice connection between concavity as well. Concavity in between -7 and 4. Concavity for less than -7. Notice the increase before -7, the increase between -7 and -1.5, the decrease between -1.5 and 4, and the final decrease for x is greater than 4. So those are all connected to each other, and they might now make the graph look a bit odd, so I'm going to get rid of those. There you go. And that should be, hopefully, a good representation for how to sketch a rational function. Thank you for listening, and have a wonderful day.